Hi, so we are now in week 9, and this is the first lecture. Basically, this is the second part of the lecture on structures. Just a bit of revision. Structures are essentially a collection of variables, and they can be possibly of different data types. This is the difference between structures and arrays. And before creating any structure variables, you have to declare a template. Basically, exactly how does the structure look like. This template provides the details of all the variables that are going to be there in a particular structure variable of this type. So for instance, if I want an integer, a float, and a character inside a structure, this is the way I declare the template. Then you can create instances of this declared structure as something like this, right? Struct sample underscore structure s1 comma s2. Also, you can use pointers to structures pretty much in the same way as you do for the other variables. Something like this. This is an example of passing structure variables to function by reference. I have C1 and C2 being pointers to the structure car, and this is essentially the same asterisk ptr syntax that we've been using for other variables. Now, there is one more operator that you should know before we move ahead. Remember that in order to actually access a particular value, a particular member variable of a structure, you can use something like this asterisk ptr, and let us say ptr is a pointer to that particular structure variable. Asterisk ptr would mean the variable itself, right? And then if you want to access a particular member within that variable, this is the syntax that you actually put asterisk ptr in parenthesis, and then dot, and then I is the member variable. We need this parenthesis because of certain precedence issues, right? This is what we know, that essentially this asterisk has a lower precedence than this dot, and so if I want this to be evaluated first, this has to be put inside a parenthesis. There is actually another uh, operator that is available to you, that is called the pointer to member operator, or informally we also call it the arrow operator. What this operator can do is it can basically make these kind of expressions a little easier to read and manage. Okay, so instead of writing something like asterisk ptr and then dot I can write it something like this ptr, and this is not really one symbol, this is basically the minus symbol and the greater than symbol, but if you put them together without a space between them, they are considered to be one operator. Okay, the arrow operator. So essentially these two statements, right, they are equivalent to each other, right? So you can see that now I don't need the asterisk part here, and I don't need the parenthesis here. This is exactly so basically this is merging two different operators into one, right? And if you've been studying C++, you might actually know that this operator has a little more to it than just accessing members. There are actually functions in C++ as well, the functions of a class, but in C it doesn't really serve much purpose other than a shorthand to access a member via a pointer. So there is something known as self-referential structures. Whenever we define these structure templates, right? Can it actually contain a pointer? Yes, it can, right? Pointers, as we all know, are just like any other variables. The only difference being that instead of storing values, they store addresses, right? And what kind of pointer variables can you have in the template? Well, you can have any kind of pointer variables. You can have pointers to integers, pointers to float, pointers to characters, as well as pointers to the same type of variables, right? The same type of variables, as in if you are defining, let us say, the node structure, it can have a pointer like this. Okay, struct node asterisk next, right? So you can see that the type of next here is basically struct node itself, right? So essentially this is a pointer that can point to a structure variable of type struct node, right? And this is actually a member of the structure itself, right? So such structures where you have a pointer within the template definition to the same type, okay, such structures are also called as self-referential structures, right? Because a variable of such a structure contains a reference to another variable of the same type of the structure, right? And in fact, it's not necessary that you have just one such pointer. You can actually have more than one as well. And if you want to read more on this, you will have to go to the additional reading slide of the presentation. We are not going to discuss that, where we have more than one such pointer, but it is possible to have as many as you want. So now, one of the most common places where these self-referencing um, is evident, right, is the case of another data structure called linked list. So we have not seen linked list, right, in the previous data structure related lecture. I told you that we'll have a look at it in the next lecture. So this is exactly what it is. So what exactly a linked list do? You can just have a look at the linked list in the following steps, right? So basically, we start by creating structure variables. Okay, structure variables are basically what? So let us say something that you create something like struct node s1, right? So s1 is the structure variable, if you remember. So so what we do is, first thing that we do is, we have a template. Let us say we call it node. Node is the common term that is used in the linked list terminology domain. A node essentially means one piece of one piece of data along with one piece of uh, pointer, right? That self-referencing pointer that we had talked about. So you create structure variables of self-referencing structure. This is the idea. Then you chain them together by storing the address of the next node in the previous node. So what we I'll show you an example soon, but the idea is, because I have a pointer that is there within the structure variable itself, I can use this pointer to point to another structure variable. So let us say I have two structure variables, s1 and s2. When I create s1, and I have that next pointer within the s1 structure variable, I can use it to point to s2. So now essentially I have chained them together, right? So if I have access to s1, with the help of the next pointer, I can go to s2 as well. Similarly, if I have another structure variable s3, and if I store its address in the next pointer of s2, then s1, s2 and s3 gets chained together, right? If I start from s1, and I start following these next pointers, I will be able to reach s3. So this is the whole concept of a chain. Okay, there is a special pointer which we call the head, right? And this head points to the first node in that list, right? So let us say if s1, s2 and s3 are in a chain, then a head points to s1. So you start from s1 and you move forward using these next pointers, and you reach s3. So the last node in the list have this next pointer set to this constant called null, right? You have used null constant before as well. It basically means that this pointer doesn't point to anywhere at all, right? So this is how we actually create linked lists. Something like this. There are, let us say, 4 nodes here. The node 50 has, the first node in the list is pointed to by head. It has the data 50. Then the next node in the list has the data 35. Then the next one has 45, and then the last one has 65. So this notation, right, this actually signifies null. It is a very common notation that you will see whenever you will have a look at a linked list. But basically this crossed pointer essentially means that this is null. It doesn't point to anywhere at all, right? And these pointers essentially mean that the address of this node, okay, it is stored in the pointer of this particular node's next member variable. Similarly, the address of this node is stored in the pointer of the next member variable of this particular structure variable. So you can see that I am trying to chain things, right? I start from here, and then if I check the contents of the next member variable, I can go here. Similarly, if I check its next member variables content, I can go here and then here. So this is basically how a linked list looks like. And let us just have a very simple example of how a linked list can have insertions and deletions. So in the beginning, the head of the linked list is just pointing to null. This is where we start off with, and then the first insertion has to be at head itself, right? There is no other node. This is the first node of the linked list. So in the first insertion, all that needs to be done is just to create a new node and put the value, whatever value was supposed to be inserted, that is put in the data part of the node, and the next pointer is just a null, right? Now this next pointer, as I have said, is a member variable of this structure, right? So this is a part of this particular structure variable, right? Whereas head is a pointer. It's a global thing, right? It's always points to the first element of my linked list, right? And usually these structure variables, we don't actually create them like struct node n1. We don't usually do that. We actually use, if you remember, the dynamic memory allocation function called malloc. That same function is usually used to allocate this memory dynamically. Why do we do that? It just saves us the hassle of managing scopes, right? You remember that something that is allocated through malloc, it is not freed until you call the free function, right? So basically you can be sure that at any point of time in your program, if a particular node has not been freed, there is no way that it is inaccessible. It is always accessible unless you explicitly free it away. So then subsequent insertions, once you have a head, then the convention is that usually you actually tell me the node after which you want something to be inserted, right? This is the idea, that you actually tell me the value with the previous node, right? So in this particular case, let us say I say that the value 35 is supposed to be inserted after value 50 in this list, right? So wherever you find 50, just add value 35 after it. This is what it says. And to do this particular insertion, the way we do it is something like this. You start from the head of the list. You check, you check for the appropriate data. Here in this case, the appropriate data is 50, and then you keep on following the next pointers, right? Basically here I find it straight away, but this is the idea, that you keep on following these next pointers and going to the next node in the list until you find the right node, right? And in this case, of course, the node was right there in the beginning, and then you simply create another new structure variable, again usually through malloc. You assign the data part to it like this, that you filled the data part with 35, and then this pointer, which was initially pointing to null, it now starts pointing to this new structure variable. Okay, and of course if we cannot find this value 50 within the list, we can actually say that I cannot insert this value because I have not found 50. This is again, right? Let us see another insertion example. Now we want to insert 65 right after 35. So here again, you'll start with head. You see it is 50, it is not 35. You move ahead, you find 35, and you said, yeah, this is exactly after which I need to insert 35. So again, you create a new node. um, yeah, sorry, yeah, that is what it. So you create a new node, and you put the data as 65, and you again, the null pointer that was there right after 35 in the 35 next member variable, it now points to 65, right? So basically we are just chaining one node with another using this next member variable. Remember that there could be a case where you have multiple nodes within the linked list with the same value. So in this case, you need to have some kind of an insertion policy. The easiest policy, of course, is that you say, I'll just insert it after as soon as I find one instance of the data, right? So in this case, I can say that had there been multiple instances of 35 in this list, 65 I will insert it right after the first instance of 35. So this is more of a policy thing, right? Now this is one more example of insertion. Just convince yourself that you understand how it works, right? So basically now I'm trying to insert 35 here. You can see what happens here, right? 35 is being inserted between two existing nodes of the linked list. So again, I start from head, I move up to 35, I create a new node, the pointers change, right? So basically this 35 which was initially pointing to 65, I have now made it point to this new node with 45, and this new node points to 65, right? So basically it gets inserted in between 65 and 45, and it's all happening through pointers. Okay, there is really no similar to the insertion in an array where I had to shift elements to the right to create space. I'm not shifting anything. These are all pointers in memory. Okay, these nodes can be anywhere in scattered in the memory. Okay, they need not be allocated in a strictly sequential fashion. They might all be at different locations in the memory. It's only the pointers that are pointing in such a way, right? So you start from here, you go here, go here, and then you finally go here. So please convince yourself that you understand this insertion. How exactly did it happen? The only thing that we have done is just manipulating a couple of pointers. Now the deletion works in a very similar fashion as well, right? So during the deletion, you actually give me the exact value that you want to be deleted from the list. So similar to insertion, you actually start browsing the list, by going from left to right, or right or top to bottom. The way it's up to you how you imagine it. Basically you start from the head and then you move forward, and whenever you find the node with the expected value, what you actually have to do is that you have to make this pointer, the pointer that was pointing to this node, right? So essentially the pointer that was in the node previous to the node that has to be deleted, the next pointer of that node now basically jumps over and points to the next node in the list. So you can simply see that I haven't really removed anything, right? It's just the pointer that has been changed. Earlier it was pointing to this node, now I will point it to wherever this value was pointing to. So I can get the next address from here, and then I just copy it here, and so then it actually becomes deleted. And then what I can do is this particular node, the one with 35, can be now freed. Okay, and how do I free it? I call the free function. So this is when I am allocating these members dynamically. And this is another deletion example, but this time because I do not have any previous node, so I actually cannot just alter the pointer. Here the node itself is the first node, the head of the list. So here all I have to do is simply move the head to the next pointer. So this next pointer was pointing here, so I actually start pointing head. I assign head to point to this particular node now, and these two nodes can now be freed. So by calling the free method. Now similar to the insertion policy, we also need a policy for deletion. So what do I do if I have, let us say, multiple instances of 50 or 35 in my list? What do I do? Again, the simplest policy is that I say, starting from the head, whichever is the first version, whichever is the first node that contains the set data, I'll simply delete it. There is some homework. Essentially the homework today is something like this. I have written the code because some of you asked me for the code, C code for stack and queue. So I had written it later and added it to the Google Drive for week 8. I'm going to add the code for linked list, a very simple linked list, all the operations that we just saw. The C code for it, I have written it, and I'm going to upload it in the Google Drive folder. I'm not discussing it in the lecture because it's a bit too long as well. So your homework is to simply read it, run the program, and understand how it works, right? There might be bugs, by the way, because I wrote it in a hurry. So if you find a bug, just drop me an email and I will change it. So this is a lecture that we are going to discuss on Monday. Thank you. Bye.